and welcome to this grade 12 lesson on functions and inverses. Now in the last lesson, if you didn't watch that one, that's where we revised what a function is and we caught up on all the basic functions that you need to remember up until the end of grade 11. Today we're going to go one step further and look at inverses of functions, and we're going to discuss how you can also restrict the domain to make an inverse a function. Okay, so not all inverses are functions, but you can make an inverse graph a function by restricting the domain. So if all of this sounds too foreign to you right now and you can't remember any of it, don't worry, because by the end of the lesson, I trust that you are going to know this stuff so well. So first, what we're going to start off by doing is give you a chance to just discuss among yourselves a little bit about inverses. Let's see how much you know quickly, and we'll come back and go through a whole summary section with you. So I'm going to give you just 2 minutes to have a look at these questions, and then you'll obviously have a better understanding when I go through the summary with you. Okay, so hopefully you have a quick idea now of what an inverse is because you've discussed it among yourselves. And I just want, in very simple terms, to discuss what is an inverse. And an inverse really is, it is a change from the original, or from an edited form, back to the original form. So a transformation takes place if we're talking about functions, which we will be doing. It's a transformation from an edited form back to the original form. So an inverse function really undoes or reverses the effect of the original. Now what you'll see on your screen is I've put up two pictures, and hopefully you'll be able to see the difference in them quite clearly. They're obviously of the same person, and some of you might recognize that as Penelope Cruz, who is quite a beautiful actress. But what you'll see, and often, you know, in newspapers and in magazines and on screen, and that these photos are often touched up. So this is a classic example of an inverse, okay? So I've got a photo, and you're going to have a look at it now, but on your left-hand side, you've got an unedited, untouched version. So this is the original, right? That's the original version, and you can see with all the wrinkles and all of the, you know, little bumps and spots and marks, and even the hands and stuff, you know, everything as it should be, as people are, because we're real, right? And then on the other side, you have the edited version, and you'll see in the middle I've put something in there, and some of you might recognize this icon. You get it on your phones quite often. It's an app. It's the UCam app, and you know, you can take any picture, use this app, and then suddenly you look absolutely flawless. So this is a classic example, really, and it's really thinking about inverses in a different way, because you have a photo, right, that's unedited, and then you go through Photoshop or whatever app that you have that then gives you an edited version. So the inverse operation will take you, if we had to undo that photoshopping and undo all that makeup, it takes you back from the edited form to the original form. So just to put inverses in a different perspective, in a different light, maybe you didn't think of it that way, but hopefully you will now. So if you look at your screen again, you'll see that on the left-hand side we have the original, going through some makeup app or going through some Photoshop and then coming out with this edited version. So your inverse takes you back to the original, okay? And it works both ways, because you can go, obviously, the other way. You can go from your original to the edited, and then you can go from the edited to the original. So your inverse will work in both ways. All right. I then said to you, give examples of inverse operations that you may have come across and state restrictions on these operations. So the classic one, we know that addition is the inverse of subtraction. And in the same way, remember I said it works both ways. So in the same way, subtraction will be the inverse of addition. There's no restrictions really there. Another one that you've come across and you've used quite a bit is multiplication and division. Now, multiplication is the inverse of division, just as division undoes whatever multiplication does. But we know that when we're looking at division as the inverse, we know that we cannot divide by 0. That gives us an answer that's undefined. All right. So if you have x, right, then 1 over x would be its inverse if we're talking about a fraction. And we know that x cannot be equal to 0 because we cannot divide by 0. It is undefined. All right. Then another classic one that we use is squares and square roots. And here the restriction is that the numbers x and y must be greater than or equal to 0. Now, if you think about it, and the reason for this is, strictly speaking, squares and square roots are not really inverses of each other unless we restrict it. So some inverses will only work with certain values. In other words, we have to restrict what we allow those values to be. And you see here that I've made a mention here, x and y have to be greater than 0 when we're dealing with numbers that are squared and then square rooted. And an example, the reason why this would be, if you look at something like minus 3 squared. So minus 3 squared, which we know is minus 3 times minus 3, that gives me an answer of 9. But I said that square rooting is the inverse of squaring. So that means if I then went square root of 9, it will undo the effect. So I'm saying what multiplied by itself twice gives me 9, and the square root of 9 is 3. So we got an answer of 3, but we started out with minus 3. Okay, and that's why we have to insert restrictions, because squares and square roots, they only become inverses of each other if we restrict the domain. So we make it work. We can make the one the inverse of the other by restricting the domain and saying, well, these are the values that you're allowed to use. These are the values that will make this work. All right. So you can restrict your x values or your squares, and you can restrict your y values or your square roots by saying, well, they're both positive values. Okay. So that means that I know that if I'm taking positive 3 and squaring it, then the square root of 9 will be 3. Okay, so then they work. So the square and the square root are inverses, but in order to make them work, we had to restrict the domain. All right? And that's just some operations that we were talking about, but then obviously we get inverse functions, which is the purpose of today's lesson. So the inverse of a function may not itself be a function. So the inverse may not be a function. All right? If the inverse of a function is also a function, we then call it an inverse function. Okay, so if the inverse is actually a function, then we call it an inverse function. So don't assume that just because your original graph was a function, that the inverse will also be a function. Okay, so this leads me to this point. Now remember from the last lesson and from what we've revised that a function will always relate each input value to a unique output value. So what that was called is one x value to one y value, or many x values to one y value. So this would be a set of your x values, which we call the domain, and then the unique output values are what we call the range. All right, and you'll remember that a function relates each input value to a unique output value. So we've got one y value for each of the values in your domain. All right. And you'll remember that we use the vertical line test to test if something is a function. So for an inverse function to also be a function, well, for an inverse to be a function, it must also pass the vertical line test. And I've given you an example here of f of x is equal to x squared. And I just want to talk a little bit more about this vertical line test and the inverse being a function. Now, what the vertical line test says is that if I have a vertical line drawn along parallel to the y-axis, and if I move it across the curve, this is not to test, remember, this is to test whether something is a function. This vertical line must only touch the curve at one point for it to be a function. So therefore, the parabola f of x is equal to x squared, yes, that is a function because this curve, this straight line, this vertical line, only touches the curve at one point at any time. Okay, so that's what we called a function. And then what you'll remember, so this is stretching you back now all the way to your grade 10 learning, is that you could get two types of functions. You could get a many-to-one function or a one-to-one function. In a one-to-one function, you had one x value for every one y value. But in a many-to-one function, you could have many x values corresponding to one y value, and that's what happens in the case of this parabola. And how you then tested whether a function was one-to-one or many-to-one is you would then use a horizontal test. So that one goes like this. So I'm going to move the vertical line aside for a sec, and let's look at the horizontal line. So I put a horizontal line through my curve. If this horizontal line touches the curve at more than one point, as you can see it's touching the parabola at 2 points. So it's touching it there and there. So that means there are many x values or different x values that correspond to one y value on the y-axis. So this is called a many-to-one function. All right? And then in the case of, for example, a straight line, if you were to do the same horizontal line test, you will see that it would only cut the straight line at one point, and so the straight line would be an example of a one-to-one function. But going back to the parabola, so I know that it's touching it at more than one point, so therefore it's a many-to-one function. Now, why do I want to bring this up? Well, if you have any function, right, like this one, the parabola, and you do the vertical line test, okay, you realize, but now you hopefully know what all of your functions are, but just in case you're doing the vertical line test, you see that, okay, it is a function. And now you need to decide whether the inverse of that graph is going to be a function. You then use this horizontal line test, which I showed you. If the horizontal line test shows you, like it did here, that you have a many-to-one function, then it means that the inverse of that graph will not be a function, okay? Because what happens in inverses is everything swaps around. So your domain of your original graph becomes the range of the inverse graph, and the range of the original graph becomes the domain of the inverse graph. So everything swaps around. So this is what I'm saying. So firstly, if I take this vertical line and I put it through the inverse. So on the right hand side we've got the inverse of the parabola, which you can see is y is equal to, all right, so we'll go into how we got this just now, but y is equal to plus or minus the square root of x is the inverse function of f of x is equal to x squared. All right. Now, if I take this vertical line and I pass it through the inverse graph of the parabola, I can see that the vertical line is touching it at 2 points. So what does that mean? That means it's not a function. Okay? It's not a function. So if, and this is where we are saying to you, if you see that you have a many-to-one function that you start out with, so your original is a many-to-one function, your inverse is going to then not be a function. All right. Because this becomes a one-to-many relation. As you can see, there's one x value that corresponds to different y values. So therefore, it becomes one-to-many. Everything swaps around, okay? So therefore, this inverse is not a function, okay? And how did we tell that? By looking at the horizontal line test, and obviously now it's drawn, and we saw it was many-to-one. So this is the point I'm making. Only a one-to-one function, right, will have an inverse that is a function. Okay, why is that important? Well, if it is a one-to-one function, then I know the inverse is a function. That means I've got to do no work on it. I don't have to restrict the domain, because that's what we're going to go into now. I don't have to restrict the domain if I know that the original graph is already a one-to-one function. Okay, however, in the case of the parabola, because it isn't a one-to-one, it's a many-to-one, we have to restrict the domain. So we'll say, well, if I was only looking at negative values for x, so from negative infinity to naught, right, then I will get a graph like this where I've restricted the domain, and just that half of the graph will in fact be a function. Or if I then restricted the original graph to only positive values of x, and then we would just get this red arm of the inverse function, well then you will once again, by restricting the domain, create an inverse that is also a function. Okay, very quickly, I just want to tell you, algebraically, in order to find the inverse, you switch your x and y values in the original equation. So if I have y is equal to x squared, I swap them around. So I get x is equal to y squared. You then take this new equation and you solve for y. So you make y the subject. So how do I do that? I get rid of the square. So I square root both sides. And I will get y is equal to plus or minus the square root of x. You first then have to check if the new equation is in fact a function. If it is a function, you will then use your functional notation. Okay, so this was a very brief summary of everything you need to know when you're working with inverses. We're going to take a quick break, and then we'll come back and have a look at some questions. Welcome back, everyone. So I hope that you've been discussing inverse functions during that break and nothing else. So we're going to go straight into our questions, because the best way to do maths is to practice it. So this is question 1 for today, and I'm going to give you 3 minutes to have a look at this question. Okay, everyone, so hopefully you've had enough time to have a look at that question. And we're talking about inverse functions, and because our first example was all about the quadratic function or the parabola, I gave you your first question on the same sort of thing, and hopefully you were able to apply that knowledge. So remember what I said before is that you will only get an inverse function if your original graph is 1-to-1, okay? And that's you find out by using your vertical line test. If the original graph does not pass the vertical line test, well, then it's not a function. But if it then proves to be a many-to-one function, which you test using your horizontal line, then the inverse of that graph will not be a function. And why it's important to determine whether the original graph is a function and whether it's 1-to-1 or many-to-one is because then that tells us whether we need to restrict the domain of your inverse. Okay, so if you're dealing with an original graph that is a many-to-one function, you will need to restrict your domain so that you get an inverse graph that is a function, and that's really what we want to get home with this question. Okay, so we need to say in the first one we're dealing with f of x equals minus 2x squared, so that's a parabola, and I'm quickly going to draw it in. All right, just a rough sketch, but it's a parabola, and we're going to have something like that. All right, and well, in fact, let me make it a little bit more symmetrical and not quite so disjoint. A little bit rounder. Okay, so you have your parabola, and that's your minus 2x squared. Okay, we know that it's not a function. I mean, it is a function, but we know that it's a many-to-one function, so we know we have to restrict the domain of this graph so that we can find its inverse function, f inverse x. Now, just a point here, you'll notice the first time we've used this notation today, really, f inverse of x, that's how we state that we're looking at the inverse. Please do not confuse this, which is the inverse, with that. Okay, those are not the same things. So some people confuse it because they think about, oh, that's an exponent, I can write it like that. Absolutely not. Those are not the same things. F of x and f inverse x, those are symmetrical about the line y is equal to x. Okay, so that's completely different from 1 over x. So how can you restrict this domain? Well, we're dealing with this graph in purple, our little parabola here, and there's two things we can do. We can either just restrict the domain of the original graph to the negative side, okay, which is this, so we can say, okay, well, let's say that x is an element from naught, from negative infinity, okay, because we're dealing with the left-hand side, so we're looking at all our negative values. So we can restrict it and say, well, let's make x an element from negative infinity up until naught. So that's the left-hand side of the graph. And in so doing, what you will then get is a graph that is a 1-to-1 function, and therefore its inverse will also be a function. Alternatively, you can restrict the domain and say, okay, well, I just want to deal with this side of the graph. And on that side, x would be an element from naught to positive infinity. Okay, and in that case, again, your graph will have an inverse that will also be a function if you restrict the domain in that way. Okay, so what I was talking about before, the line of symmetry, which is y is equal to x, I'm going to just put that line into our graph, and remember your two lines are symmetrical about this line, y is equal to x. So I've just drawn in our line of symmetry when we're dealing with inverses. All right. So there's two things you could have done here. Your answer could have either been, okay, I can restrict it to the positive side, or I can restrict it to the negative side. The next part says, well, if the domain is restricted such that x is an element from negative infinity to naught. So in other words, we are just looking at the negative arm of the parabola. Okay, so we're just restricting to that domain. Sketch f of x and then the inverse on the same system of axes. All right, so the inverse graph, now remember everything swaps around when you deal with your inverse. Your domain of the original becomes the range of the inverse, and the range of the original becomes the domain of the inverse. Everything swaps around, okay? So this, if I'm restricting to x as an element from negative infinity to naught, that's going to become the range, so it's going to be y as an element from negative infinity to naught. That is going to become the range of the inverse. All right, so that's going to become the range of your graph. So what you're dealing with here is, say you take a point on your inverse graph, which is x is minus 2 and y is minus 1. Well, on the other graph, on the inverse graph, it's going to swap around. Your coordinates are going to swap around. So on your inverse graph, when x is minus 1 and y is minus 2, you will then get a point on the graph. So that's that point there. All right, and that's going to help me to sketch this graph. So this is going to be a graph that looks like this. And I'm going to take off the side of the parabola we don't need because we're only restricting to the negative arm of the parabola. So that's that part. And we'll put our inverse in pink. So it's going to be a graph that passes through the point when x is minus 1, y is minus 2, so it's going to go like that. All right, so that's going to be the graph f inverse of x, and it is a function. And please remember this, that you can only put this f in, f of x. That's called function notation. You can only use this if your inverse is a function, because this is called function notation. Okay, so it implies that the graph you're dealing with is already a function. So you can only use that function notation if your inverse is in fact a function. All right, so you saw here how we could restrict the domain just to the negative arm so that we could have an inverse graph that is a function. If you did it to the positive side, you will arrive at the same conclusion. All right. Okay. Now, the other thing that we're going to discuss in today's lesson, because we are talking about inverses, is the exponential function, because the exponential function has an interesting function which we haven't come across yet called the logarithm. All right, so we're going to look quickly at exponential functions because we need to discuss logarithms. So just a reminder that your exponents, your exponential graph, is a graph of exponential growth. Okay, it's either showing exponential increase or exponential decrease. So what I've got on your screen is an increasing exponential graph where you can see y is equal to 2 to the x. So we've got a whole number base and we've got an increasing graph. A reminder about increasing graphs. What does increasing mean? It means that as x is increasing, so as your x values are getting bigger, your y values are also increasing. So if you look at your graph, as we're going to the right on the x-axis, so your x values are getting bigger, your y values at the same time are also increasing. So that we call an increasing function. Okay? Then on the other side, symmetrical to the increasing exponential graph, symmetrical about the y-axis, you get the decreasing exponential graph, and there you'll see we're dealing with fractional bases, all right? So that implies that you're going to have an decreasing exponential graph. It's decreasing, we've got a fractional base, so that means as x increases, so our x values always increase as we go to the right, the y value will start decreasing, and you can see that happening because as your x values are getting bigger and bigger, you can see you coming lower and lower on the graph, so your y values are decreasing. All right, so that's just a reminder of the two different types of exponential graphs you can get, and obviously the important thing for today's lesson, the exponential function can be reversed by the logarithmic function. But before we talk about the logarithmic function, we need to define what a log is. Okay. Now, A log, there's lots of different ways you can say it, but I really want to look for the easiest way to say it. And the important thing we want to get to today, so I'm not going to go through all of the calculating using the log laws and that's not for exam purposes. We really want to look at the log function and how that relates to the inverse, so how it is the inverse of your exponential function. There's different ways you can think about logs, but they all amount to the same thing if you phrase it correctly. And I like to think of a log as another way to write an exponent, okay? So there are your formal definitions, but just think of it as the log is another way to write an exponent, all right? The log of a number, if you're looking for the formal way, is the exponent to which the base of the log must be raised to produce that number, and it is the inverse of exponents. So if you have any exponential function, so like y is equal to b to the x, right? Obviously we know b, it has to be, well, we're dealing with a log, so it's got to be greater than 0. You cannot take a log of a negative number, so therefore we restrict b. b has got to be greater than 0. We can then change from exponential form to log form. And remember what we said is we said that the log is another way to write an exponent. So if I was using this to change, I've got y is equal to b to the x. So this is an or. This is not an equivalent statement here. So we're not saying that gives us that, okay? Those are two separate things. But if I had y is equal to b to the x, and I want to change that to log form, I said it's another way to write this exponent, so that means x is going to equal something. X is going to be equal to log of your number y to your base b. So your base of your exponent is also the base of your log, and so this is a different way we can write the exponent, all right? The definition for your log is y is equal to log of a number to some base. Again, b is greater than 0. Okay, and then in the next line, I'm just showing you again that if you have any number raised to a power, you can rewrite the power, and that's just from exponential form into log form. Some restrictions here. Your number a has to be greater than 0, and that's because log is undefined for any negative number. A is not equal to 1, and the reason for that, well, if you're looking at your exponents, we know that any exponent, if we say 1 raised to any power at all, anything, the answer is always going to be 1. And log of 1 is always 0. Okay, because remember, it's another way to write an exponent. So I can also say anything to the power of 0 is equal to 1. So they all relate, they're all inverse. So therefore, if anything raised to the 0 is 1, we know that log of 1 is always going to give me 0. That means I can't really go anywhere with anything. So we've got here log base a has to be greater than 0, a cannot be equal to 1, and b has to be greater than 0. This also goes back to your log laws, which I don't want to go into too much detail with, but we can rewrite this as x is equal to log b over log a. And if you've got log 1 in the denominator, you're dividing by 0, and that's undefined. So that's just explaining some of the restrictions to you. All right, so this is really why we have these restrictions, but it's not something where you've got to now go and practice these laws. How do I rewrite the logs and that? No, no, no. That's not for exam purposes, and that's not the point really for today's lesson either. We just want to look at how we can then use this with inverses and use it with exponential graphs. We're going to take a quick break, and so when we come back, we'll look at how we can write from exponential into log form, and we'll quickly discuss your log and exponential graphs. Back after this. Welcome back, everyone. So we were talking about logs, and we were talking about exponential functions, and we want to show how the exponential function and the logarithm are related. Okay, I quickly want to do an example of converting from exponential to log form, because that is something you need to know how to do, especially for your functions. Okay, remember I said to you at the top of this that the log is a different way to write an exponent. So if I have 5 squared is equal to 25, I know that 5 to the power of 2 is equal to 25, but the power, which is 2, or the exponent, which is 2, okay, that is, we know the exponent with a base 5, and we know that 5 squared is equal to 25. But 2 is also the log of the number 25 to base 5. So we're saying if we write it in this form, so how did I do it? It's my exponent is equal to log of the number, or your answer on the right hand side, with the same base that you had in your exponent. All right, so 2 we can rewrite as log 25 base 5. Okay, and sometimes you'll see just log x like that. When it's given in that form, your base is 10 and we don't write it in. Also, when you're using on your calculator, you know, on your calculator you've got that log button. That log button also has a base 10. Okay, so that was just a quick discussion about logs, and now we're going to look at the logarithm function. Okay, so again, we know that, and we've said this before, that we know that the log graph is the inverse function of the exponential function. So your exponent graph was 1 to 1, so therefore it has an inverse that's also a function. So on your drawing on the left, y is equal to 2x. That is drawn in for you in blue. That is your exponential graph. You've got your axis of symmetry in green. Your line of symmetry y is equal to x. So these are symmetrical about that line. They are equidistant. And then if we change from exponential to log form, so we're going to have log of y is equal to log base 2 of x, and that is your log function. So you see that your base again is still the same as the base of your exponent. So it's log base 2 of x will give you your log graph. We know that this is an increasing exponential function. So our log graph here, this is also an increasing log graph. Then you see on the other side you have a decreasing exponential function. Y is equal to a half to the x, and that graph is decreasing. And then the inverse of that is y is equal to log x base a half, and that would be your decreasing exponential function. All right, how did we get these values for the log graphs? How do we know what their equations are? Well, if I have y is equal to 2 to the x, all right, my rule says swap x and y. So I'll then have x is equal to 2 to the y. All right, that's what you've got. So I'm looking now algebraically for the inverse. Okay, so I swapped x and y's, and now I've got it in this form, and now I need to get to the exponent y there, and that's when logs come in, because now to convert this into a form that I recognize, I can rewrite the exponent y as log of my number with a base 2. Okay, so that's where those equations come from. That's how we got those inverse equations. Okay, and because I feel like we are running out of time, I want to quickly give you a chance to have a look at a question, and I want to give you a chance to sketch these graphs for yourself, the exponential graph, and then the inverse of that, the log graph. I'm going to give you 3 minutes to have a look at this. Okay, welcome back, and hopefully you managed this question very easily with everything we've discussed so far. Let's go through this one in detail. So I asked you to draw an exponential graph, an increasing exponential graph. How do I know it's increasing? Well, the base is a whole number, right? And I then asked you to draw the inverse of that will be an increasing log graph. How do I know that both graphs are going to be functions? Well, we know that 3x, you know the shape of that looks like that. And if you were to get a vertical line and, a horizontal line and run it through this exponential graph, you will see it only cuts it at one point. So that means it's a one-to-one function. Therefore, the inverse will be a function, so I don't need to restrict the domain. Okay. So if f of x is equal to 3x, find the inverse of f and sketch both graphs. So I'm going to start with finding the inverse, and this is an algebraic method. So I've got y, I'm just rewriting it so it's easier for me to convert. Remember, f of x, an easier way to write that is y. So if I've got y is equal to 3x and I want to now find the inverse, what I do is I swap x and y. So I'm going to get x is equal to 3 to the power of y. I then solve for y. In other words, I make y the subject of the formula of this equation. How do you get to that y? Well, it's an exponent, and I know that log is another way to write an exponent. So I can say the exponent y is equal to log of my number x with base 3. All right, and this is the inverse function of f of x is equal to 3x. So this is your inverse function. Some other points about f of x is equal to 3x. We know that the domain of that is x is an element of real numbers. Y, your range, is greater than 0, but y is not equal to 0. So what you'll see is in your exponential functions, your x-axis is an asymptote. So it's a line that the graph never really touches. The important point on an exponential graph, which we always mark down, is your y-intercept. So when x is equal to 0, your y-intercept is 1. How did I get that? Well, y is equal to 3 to the power of 0. So y is equal to 1 when x is 0. So I plot that point on my graph, and you can put in another point if you would like. It's not necessary, just for accuracy you can. And then you join your points up, showing that the x-axis is an asymptote to your exponential function. Mine is not quite smooth, but it's because I've got shaky hands. All right, so we've got y is equal to 3 to the x, and that's my exponential function. We know that these are symmetrical about the line y is equal to x. Okay, so these are inverses, and we have that all the x and the y values swap around. Remember, I said that to you when we were explaining how to do our log and exponent graphs and our parabolas as well. Your x and your y values swap. So if the y-intercept on the exponential graph is 1, it swaps around. That means the x-intercept for the log graph is going to be 1. Okay, where in the exponential graph you had a point x is 1, y is 3, on the log graph you'll have x is 3 and y is 1. Okay, so everything literally swaps around. It's an inverse. You swap x and y values. So to draw this, it's going to look something like that. Again, forgive my drawing skills. All right, and that's going to be, actually I need to redraw that. That's not looking very, very nice. Let's just put that in again. Okay, so my log graph is going to go something like this. All right, and those are inverses, and they're symmetrical about the line y is equal to x. And what you'll notice, like we said, your y-intercept becomes the x-intercept for your log graph, and also your domain and range swap around. So here you'll have that, again, you see, going back to this, we noticed that for the exponential graph, x was an element of reals. Well, here it's going to be y is an element of reals. okay, where we had there that, what did we have? We had y was not equal to naught, so here we're going to have x is not equal to naught. So in other words, we're going to have no y-intercept. Okay, so everything swaps around with those two graphs, and it's really just a matter of practicing drawing these graphs. Obviously, yours will look much better than mine. I'm not very good at art, so, or drawing for that matter, so mine look a bit skewed, but yours, you'll have a few points that you'll plot on the graph to make them look more symmetrical. They're symmetrical about the line y is equal to x, so that's where you get one graph being the inverse of the other. And one of the important things here, which you often get asked, is to algebraically find the inverse, and that's where you have to swap the x and y and then make y the subject of the formula. So just to quickly recap what we did in today's lesson, we saw that the inverse of a function may itself not be a function. If the inverse of a function is also a function, we refer to it as an inverse function. Okay, and remember, you can only use functional notation when your inverse is also a function. Also, importantly, only one-to-one functions will have inverses that are also functions. If you had a many-to-one original function, then you have to restrict the domain to get an inverse that is also a function. We saw that when we were talking about the inverses with our log and exponential graphs, that a log is another way to write an exponent, and the exponential function can be reversed by the logarithmic function, just in the same way that a log function can be reversed by an exponential function. So it's a lot of things that you do need to practice, especially with your logs. Remember, when you're dealing with logs, those rules and laws and manipulating, those are not really for exam purposes. It's just really more for your understanding. What you really want to take out of logs is how it relates to the inverse of the exponential graph. That's it from me, Natasha. Until next time, cheers.